Picture yourself watching a video and asking a simple question. How far is that heater from that door? A human eyeballs it in a second. But for a vision language model, this innocent question unfolds into a chain of geometric operations. Figure out which pixels are the heater, which are the door, lift them into 3D, and measure the shortest distance between the 2-point clouds. Miss any step or pick the wrong notion of distance, and you're off by meters. This kind of spatial reasoning, which underpins robotics, embodied AI, and video understanding, remains one of the most stubborn weaknesses of even frontier vision language models. The paper we're looking at, called SpatialClaw from NVIDIA and KAIST, argues something subtle but important. The bottleneck for tool-augmented spatial reasoning agents isn't which perception tools you give the model. It's the action interface, meaning the medium through which the agent invokes those tools, inspects their outputs, and decides what to do next. Think of it like the difference between giving a chef a fixed menu of pre-made sauces versus giving them a full kitchen. Same ingredients, radically different range of dishes. To ground this, consider the two dominant approaches before this work. The first is single-pass code execution, where the agent writes one complete Python program up front, runs it once, and hopes for the best. This is expressive, but the agent is essentially blindfolded, committing to a full analysis strategy before it has seen a single intermediate depth map or segmentation mask. The second approach is structured tool calls, where the agent picks from a predefined menu of named tools, filling in typed arguments in something like JSON, and receiving typed outputs back. That gives you inspectability between steps, but the composability is limited. If a task requires chaining a depth estimate with a segmentation mask in some idiosyncratic way, and that composition wasn't anticipated by whoever designed the tool schema, you're stuck. SpatialClaw's proposal is what the authors call code as the action interface. At each step, the agent writes one Python cell, which is executed in a persistent Python kernel that stays alive across the entire reasoning trajectory for that example. Every variable produced, every segmentation mask, every point cloud, every camera pose sticks around as an ordinary Python object that later steps can inspect, compose, or revise. The kernel comes preloaded with the input frames, a handful of perception primitives like a depth and reconstruction tool wrapping, depth anything 3, and a segmentation tool wrapping SAM3, plus the full scientific Python stack, meaning NumPy, SciPy, and Matplotlib. Crucially, the agent can call a show function that renders an intermediate image back into its own context on the next turn, so it can literally look at the mask it just produced and ask itself whether it looks right. The outer loop is a 5-stage cycle. First, a planner, running as a separate language model session without access to the images, reads the question and the tool documentation and drafts an analysis plan. Then the main agent generates a Python cell containing 4 structured fields: a purpose, its reasoning, the next goal, and the actual code. That code is passed through a security check that parses its abstract syntax tree to reject unsafe operations, then executed in the kernel. The results are assembled into feedback consisting of standard output, summaries of newly created variables including their types and shapes, any tracebacks from errors, and any images the agent registered via show. This all flows back into the context, and the loop continues until the agent submits an answer through a special return answer function. The whole thing is training-free, meaning no fine-tuning, and it's guided entirely by a unified system prompt that encodes general spatial reasoning discipline, things like preferring metric computation over pixel intuition, checking multiple evidence sources, and using medians rather than means for robust aggregation. The results are striking. Across 20 spatial reasoning benchmarks spanning single image geometry, multi-view reasoning, video and 4D dynamics, and general video understanding, SpatialClaw hits 59.9% average accuracy with a Gemma 4 31B backbone, beating the recent Space Tools agent by 11.2 percentage points. And these gains generalize. The same system, with no per benchmark or per model tweaking, delivers consistent improvements across 6 different backbones ranging from 26 billion to 397 billion parameters, spanning both the Qwen and Gemma model families. The biggest wins concentrate in exactly the categories you'd predict: multi-view reasoning, camera motion, and dynamic 4D video tasks, where the analysis requires chaining geometric operations across frames and viewpoints in ways that no fixed API schema could anticipate. Two ablations really sharpen the story. First, when the authors strip out all the predefined utility wrappers, keeping only the raw perception tools plus NumPy and SciPy, performance barely drops. This means the value isn't in a clever library of handcrafted spatial helpers. The value is in the interface itself, in giving the agent the freedom to compose arbitrary numerical operations against persistent intermediate state. Second, and this is genuinely delightful, when they analyze which primitives the agent invokes across question types, they see clean, spontaneous specialization. Distance questions naturally attract KD tree nearest neighbor searches and vector norms. Direction questions pull in dot products and cross products. Nobody told the agent to do this. It emerges from the semantics of the question and the flexibility of the interface. Now for the honest limitations. Failure analysis shows that geometric reasoning errors remain the leading failure mode, meaning the agent often has good perceptual evidence but botches the 3D math, the coordinate transforms, or the projective geometry. Perception errors also matter, driven partly by the underlying VLM hallucinating objects that aren't there, and partly by the perception tools themselves being imperfect. There is also a class of failures where the agent detects an inconsistency but can't recover, either committing to a flawed early hypothesis or oscillating without converging. Latency and cost are also real concerns the paper doesn't dwell on. Running up to 30 steps per example, each involving a large VLM call plus potentially heavy perception model inference, is expensive. And the security sandbox, while sensible, means the agent can't easily reach for arbitrary tools that might genuinely help. Now let's walk through some questions you might have after hearing all of this. First question, why does keeping state in a persistent kernel actually matter so much? Couldn't the agent just rerun its earlier computations? In principle, yes, but rerunning depth anything 3 or SAM3 is expensive, sometimes taking seconds per call on a GPU. More importantly, persistence changes the reasoning pattern. When the agent knows a variable is still there, it treats intermediate results as durable evidence it can revisit, cross-check, and compose. Without persistence, the agent tends to inline everything into a single monolithic computation, which is exactly the single-pass failure mode. Second question, if code is so flexible, why bother with any predefined tools or utility wrappers at all? The ablation actually shows that the utility wrappers contribute very little once you have the core perception primitives and scientific libraries. But those core perception primitives, the segmenter and the reconstruction tool, are irreplaceable, because they encapsulate large neural networks that the agent could not implement from scratch inside a Python cell. The lesson is that you want a small set of heavy-hitting perception primitives plus a fully general composition environment, not a big menu of narrow helpers. Third question, doesn't giving a language model arbitrary Python execution open a Pandora's box of security and reliability issues? Yes, and the paper addresses this with a static, abstract syntax tree checker that rejects file I/O, network calls, dynamic evaluation, and other risky patterns before the code ever runs. There's also a per-cell timeout and a kernel restart mechanism if things go wrong. On reliability, the paper leans hard on treating every runtime error as just another observation. A traceback becomes feedback the agent can react to on the next turn, which is very different from a fixed API where an unexpected error just crashes the pipeline. To bring this back to the world of large-scale recommendation systems, the ideas here transfer more directly than you might expect. Modern recommendation pipelines increasingly involve agentic components for user understanding, query reformulation, and multi-stage reasoning over rich user context. The core insight that a persistent, stateful workspace with flexible composition beats both single-shot programs and rigid tool schemas applies whenever you have specialized retrieval, ranking, and feature computation modules that need to be orchestrated in query-dependent ways. Imagine a candidate generation agent that can pull embeddings, run similarity searches, apply business rules, cross-reference user history, and iteratively refine its candidate set with intermediate inspection at each step. The type tool call approach forces you to anticipate every composition up front, which doesn't scale to the long tail of user intents. More concretely, for real-time serving, you'd probably compile the most common code patterns discovered by the agent offline into optimized execution paths, using the flexible interface primarily for tail queries or for offline user modeling where latency budgets are looser. And the spontaneous specialization finding, where the agent selects different primitives based on question semantics without being told to, hints at a way to automatically discover query taxonomies and their appropriate retrieval strategies just by mining what the agent naturally does across a large query log.